Hi, class. I want to talk about another couple of applications of the normal distribution for finding probabilities and how we can use that to convey information or make decisions in certain instances. What I'm going to do is move this away at first. And the first thing I want to talk about is a confidence interval. And give an example. Let's say that we were looking at gas mileage claims for an automobile, and let's say that a Dodge Caravan had claimed that their cars would get, on average, or their minivans, would get 28 miles per gallon on the highway, right? And that sounds pretty straightforward, and it may not be an issue. But in a way, it does create a problem because people, when they buy vehicles, gas mileage is important for most of them, and especially when gas prices are very high. And if somebody was really focusing on this particular vehicle, and they saw, okay, I was getting 28 miles per the gallon, and that's for a van. We'll say, okay, that's pretty good. And then they purchase the vehicle, but they don't get 28 miles to the gallon on a highway, and then they would maybe get frustrated over that because again, this is what they expected, but maybe they were understand they weren't understanding this, or at least using this what we refer to as a point estimates. uh, okay, using a point estimate is maybe not the best thing to do in this case. And what we would typically think here is that the 28 was representing average. So, what was the average miles per gallon that someone was getting? So, in other words, then there's probably a real true range of values when we look at the miles per gallon on the highway that people get. So, by thinking that everybody gets 28 miles to the gallon on the highway, right? That's where a point estimate can be misleading. And we do, if you drive around and you have, different automobiles and you've driven them and looked at the claims and that, and a lot of times you see that they're different than what the average or the center of the distribution is. So if we say this is the mean, then how many people are going to get less than 28 miles to the gallon on the highway? And we would say, well, half of them. The mean we assume is in the middle, and so that means 50% of the people are going to get less than this and kind of be upset. So that's why I'm saying that it's not a good idea to use a point estimate in this particular situation unless the variability was very, very small. So what we could do is use something else. Now, if we would have said that the miles per gallon on the highway, uh, the miles per gallon on the highway was between 21 and 34, say something like that, then if someone bought the vehicle and they got, say, 22 miles to the gallon on the highway, then they would say, okay, well, it says that's what I got. Maybe they won't be happy about it, but they won't be like saying that they were misled because it clearly states here that, most people are getting 21 to 34. And then some are a little less, some are a little more, but this is basically what we refer to as an interval estimate. So an interval estimate gives a clear idea of where most people would fall, not a point estimate. And again, point estimates are okay depending on how you're applying them. And we're just saying that, is an interval estimate always better than a point estimate? No, we're just saying that in some situations, they absolutely convey information about what someone's interest, might be. So if we, again, are talking about gas mileage and we want to buy a vehicle, we would really want an interval estimate rather than a point estimate in that case. So what we need to find out then is, okay, interval estimates, again, are good. And in, particular situations, we really should be using those. And so we want to talk about, though, how do we create point estimates and what are our options, right, with point estimates, and how does probability tie into the creation of those point estimates? Okay, so let's clear that out. And then, so let's say that we did work with this mean and we said, that the mean was equal to 28. Okay. And then something else here, we're going to say that E is equal to 2. All right, so again, I just kind of made this up. This is the standard error estimate. Okay. Sounds like standard deviation, right? Or standard error, but this is a standard error of estimate. So I have the mean equal 28. I want a confidence interval, okay? I want an interval estimate, and we're going to create a particular type of interval estimate called a confidence interval. Now, when we were talking about the empirical rule, when we started talking about the normal distribution and using it, and we talked about the empirical rule, I'm just going to back this up a little bit and go back to that. And remember when we set this up and we said the standard normal distribution, if we went up to 1 and down to -1, that 68% of all the values would fall plus or minus 1 standard deviation of the mean. Right? So we're kind of creating an interval estimate here, right? We're creating interval estimates. If we go up to 2, down to -2, from -2 to 2, 95% of all the data values should be in this interval, right? In this interval. And remember that plus or minus 3 was 99%, and then that was our empirical rule. So we, in a sense, already had talked about interval estimates. A little bit differently, though. We want a very specific application, but this is all still really what we're talking about here. So we're not throwing this out or really changing it dramatically. We're using the same idea here. Okay. Yeah, get that out of there. Okay. All right. So we're going to do again, same thing in a little bit different way. So to create a confidence interval, which is not the empirical rule, it's based off of the empirical rule, but it has to deal with sampling distributions like we had talked about earlier. And this is a very simple idea, right? We're going to take 28 and we're going to put it in the middle here. Okay, so there's my middle, there's the mean, the middle of my distribution. And we're going to take and add the error. Okay, so that's 28 plus 2. And then we're going to subtract 28 minus 2. Okay, so of course this is going to be 26. 28 plus 2 is 30. And there's my confidence interval. All right. And I know you're probably thinking, all right, that's the easiest thing like we've ever done in statistics, right? And it again, it's pretty straightforward, but this is very simple. And I know you're maybe thinking that, well, it can't be quite that easy. Well, it is, but this right here, see, I haven't told you how I got this. So this is really where we have to spend the time with confidence intervals, because actually creating the confidence interval itself is very straightforward. Take your mean plus your error, your mean minus your error, and that's it. So we would say that instead of the average gas mileage based off of our sample data, the gas mileage, right, mean could be somewhere between 26 and 30, right? So we're trying to capture a population mean and give us an idea of like the range of where that could actually be in, right? So is this really, going to help us on an individual basis? Well, actually, you know, not really. We're not talking about the empirical rule again. I want to emphasize that is that we're talking about sampling distribution. So if we're looking for the population, true population mean, we basically have it in here. Okay. All right. So let's go ahead and get rid of that, and we're gonna I'll just take that all off of there. Okay. All right. So let's say that we have again. We have a mean of 28 and a standard deviation. And let me again erase that. Whoops, back this up. We have an idea that the mean is 28, and we go out. We're going to sample. Okay, we're going to click the sample. So I'm using X bar. Our sample mean X bar is 27. Our standard deviation is 4.2. And our sample size is, we'll say, 35. Okay. So again, this is from a sample, right? Sample data. Now what I want to do again is I want to create a confidence interval about this 27. And so we're going to take, and eventually what we're going to do is we're going to take, right, we're going to put 27 here in the middle in a sense, and we want to add and subtract something to it. We want 27 plus some error, right? 27 minus some error to get that confidence interval. And I mentioned really what we need to focus on is, okay, how do you get that error? Okay, so E is equal Z times sigma over the square root of N. All right, that's kind of our theoretical, right? Our Z distribution, our population symbols you notice I have in here, right? So now E equals 2. So what is the Z value here? And that's one of the first things I want to talk about. This Z value is actually off your Z table. And this has to deal with that empirical rule. So if we were looking at plus or minus 2 standard deviations, which captured 95%. So when I showed that empirical rule, again, I did plus or minus 1 standard deviation, captured 68%, plus or minus 2 standard deviations, captured 95%. So if we're doing a confidence interval, the most common one is a 95% confidence interval. So we need to be able to identify that first, right? So 95% confidence interval. Right? So we could put 2 in here. Now, it's approximate. The actual value off the table is 1.96. Okay, so 95% confidence interval, the z value is 1.96. Okay. Well, the standard deviation, okay, we have our sample here to approximate that. That is 4.2 divided by the square root of n35. All right, so, and if you remember, this right here is our standard error. When we work with sampling distributions, we don't use the standard deviation of a sample. We use the standard deviation of a sampling distribution. So a bunch of samples, parameters, and or values, and so we're estimating that, right? All right, so let's see, error equal to, so we got 1.96 times 4.2 divided by, divided by square root of 35 . There we go. You got to be careful on those parentheses. All right. Enter. Okay, 1.39. So we get over here, okay, 1.39. So this is the E, then that's how we get that. So 27 minus 1.39, 27 plus 1.39. And then again, we have to subtract that and add it 27, 28.39 and 25.61. So from here to here, right, there's our 95% confidence interval. And let's keep this information up there. I just want to show you, right? We always kind of go for the technology here. Let's see what we got. So we're going to do, clear this out. We're going to go to stat, tests, and then down to Z interval. Okay, Z interval. Hit enter. Again, this is standing for confidence interval using the Z distribution. Yeah. So we're inputting here the statistics, and the standard deviation was 4.2. The mean, 27. And N is 35. C level is 0.95. What's there? Calculate. And again, here's 25.61. If you look, here's 25.61. up to 28.39 or 28.391. Right, so there's my interval from here. Here's my lower limit and my upper limit confidence interval. So the calculator makes it pretty straightforward. You can do confidence interval, you see Z. Let's do one with the t distribution, and I'll talk about that as we go through. Now, I'm going to change this. If I left it and I went over to tests, now if I went down to t interval here, I'd still get basically the same answer. Okay, but it would be a little bit different. Let's go ahead and try it. T interval, enter. My mean's 27, standard deviation 4.2, 35, 95%, calculate. And you'll see, remember it was 25.609. Now I got 25.557. So it's almost exact. It's off just a slightly. The other end's off slightly, right? So what happened there? Well, not a big deal, but remember that the Z and the T distribution are pretty identical once the sample size gets large. Now, we have 35 for a sample size, and it's pretty darn close. So when should we start using the T or the Z? Well, the reality of it is just always use the T distribution, and then it'll be the right value. Don't guess at 30 or whatever. Sometimes the textbooks will say, oh, over 30, use the T, under 30, use the Z, or over 30, use the Z, and under 30, use the T. But we see here, even at 35, it's still off a little bit. Even at 40, it would be off a little bit, and so on, if you use the Z. So that 30 rule is just a really, really, kind of not very exact, unexact point. So just use the t distribution. So otherwise, let's go and do another problem. And we're not going to worry about whether we should use the z or the t. Okay. I'm going to put this down for a minute and clear this. All right. So let's say that we have a sample mean of 55 and a sample standard deviation of 15 and equal to 100. And again, this is a sample that you collected, right? So sample data. And so why did we collect the sample? Well, I mean, for whatever reason, it could be anything. But basically, the idea is that you're maybe making a decision that, see, this X bar is a point estimate. And you're thinking, well, I'm estimating the population mean. And maybe that's, I need to know how close I am. Because again, if I'm working with a lot of variability, this says S is 15, you may think that's too much, because I want to be able to give people a pretty good, accurate estimate of where the actual population mean is. So you decide that you want to create a confidence interval. Now let's go ahead this time with let's create a 90% confidence interval. The typical confidence intervals are 90%, 95%, 99%. Now the associated z-scores with those are 1.645, 1.96, and 2.575. And the confidence interval z-score, okay. Now, 95 is the most common. Again, obviously, if you want more confidence in your results, you're going to have to spread that interval out a little bit more. So they're saying to multiply that standard error by 2.5 times instead of roughly 2 times. If you only need 90% confidence, then see, you can make the interval a little smaller, 1.6 times, right, instead of 2. So these are just some options, and these are very standard. You can put any confidence interval. You can create any size confidence interval that you want, but that doesn't usually happen. So usually in the books you'll see, something like this written. But if you don't have a large enough sample size, then you can't use these scores. Just like in that last example at 35, if we would have used, right, we were off a little bit. The T makes the adjustment. Now, we don't have to worry about the T table if you have the calculator. So otherwise, what we have to do is take and say, whatever the T score is going to be, 1.7, 1.8 or something, the sample size is fairly large, so it's going to be pretty close to this. Let's just go ahead and, we're going to have some kind of interval at the end where 55 is going to be in the middle, and we're going to need a value here and here, right? So we can just go to the calculator. Let's clear this out. Let's go to stat, tests, T interval. Okay, so this is trying to find or build a confidence interval about a sample mean. Enter. So the mean is 55, standard deviation 15, and sample size is 100. Confidence interval 0.90. Calculate. So we're at 52.51. And 57.491. So we could round those a little bit again. We have 52.51, 57.49. $57.49. Okay, so here's our interval, confidence interval again. So what we're saying in this particular, example, we can use this in different ways, but what I'm showing, what they have in the book basically is that the population, the true population mean, is it here? Is it up here somewhere? But we're saying it's in here somewhere. Okay. Because when you collect a sample, the odds that you got the exact middle of the distribution, the true population proportion correct, right? We're saying 0, theoretically 0. So this number we know is wrong. Well, where might it be, right? Well, we're saying we're pretty confident it's right in here between 52, 57, somewhere in here. Okay. Now let's say that you don't like that, right? That error is too much. Well, how much error is there? So we have the distance from here to here, right? We're going to call that, because remember we talked about the standard error of estimate before, which was this distance from here to here. That was the E. that we were adding, taking from the middle, adding it, and subtracting it. So what is our E? Well, it's just 57.49 minus 55, right, in the middle. So we get 2.49. So our E, right, in this case is 2.49. Let's say that's too big. Let's say that we want it to be 1.49. Is there anything we can do? So again, we have an E of 2.49. And let me just use this eraser. Okay. Get some room here. All right, we're going to keep that there. And I'm going to get rid of these. Now, one thing you can do to control a little bit of the error is increase your sample size. So we have a sample size estimate. Okay, sample size estimate. It's N equal to Z times sigma over E squared. This is a Z. This is again back to that confidence interval. All it is the formula for a standard error of estimate solved for N. It's the same formula. It's just solved for N. So let's take a look at what we got here. Now, let's say that this 2.49 is too big. We want it to be 1.4. So see E, I don't want to put 2.49 in here. I want it to be smaller. So we have N equal to, all right, we had a 90% confidence interval. That was 1.645. Standard deviation was 15. E, we're going to make it 1.49. Cut that down by one whole unit. Okay. 1.49. And then just calculate it. So let's see what we got. So we have, and whoops, let me just, did I put the, let me just, forgot the square here. Yeah, right here. Squared. There it is. All right, so we're at 1.645 times 15 equal to, all right, that's the numerator here, divided by 1.49. All right. So that's what's in here. And I'm going to square that. 274. All right, so 274, I'm gonna put this down. Come back over to here, 274. So in other words, I had a sample size of 100. I didn't like the error. It was too much. I cut it down a little bit from 2.49, right, to 1.49. Well, it's telling me here that if you really want to cut your error down, then you're going to have to sample, look, almost 3 times as many. You got 274 So you run a sample, it'll give you a little better estimate. And that kind of makes sense, theoretically speaking, as long as the sample is representative, then yes, a larger sample size will reduce your standard error. So that's what we were shooting for there. Now, I want to do another problem here with confidence intervals. Let's go ahead and clear that out. Now you can make confidence intervals about any statistic. So let's go ahead and talk about a population proportion. So let's say that we have a population, or I'm sorry, a sample proportion equal to 0.36. So we collect data, we have n equal to 500. With proportions, we typically have larger sample sizes. Let's say that we sampled 500 people on whether they believed, that we should go back to, this non-social distancing in this pandemic. And so 36% said, yes, we need to return to the way things were. And you think, okay, well, this is sample data again. So you went out and you collect a sample. This is not anything to do with a mean or standard deviation, right? All I have is a qualitative data. They're just responding yes or no, okay? So your sample data, you asked 500 people, 36% said yes, but that's not going to be the exact population proportion of all people. If everybody was asked whether they want to go back or not, it's most likely not going to be exactly 36%. But can we get an idea on the range of possibilities of what that true population proportion is? And yes, we can build a confidence interval, right? Let's say we want to have a 99% confidence interval. And what we're going to do again is go right to the calculator. So we don't have to figure anything out or whatever. Let's go to the calculator here. And clear this. So again, for a sample proportion, I go to stat tests. And I'm going to go down to one prop z interval. So proportion, since this is a proportion here, we go over here to the proportion z interval test. Now x is 15, n is 27. Let's see. Okay, well that's not it. We don't even have an x here. All right, so what they're asking here basically is the mean, but it's saying how many values did you come up with? Not the percent. See, they're not asking, they're saying how many. Well, how do we got to take 36% of 500 because 30.36 times 500, that's 180. So we're saying 180 out of the 500, right? Not what percent, again, the count. And then 500 was the sample size. 99.99 for confidence interval. Calculate. So our confidence interval goes from about 31%, we'll say 30% up to about 42%. So over here again, the 30 to 42, we'll round it off again, we'll round it off. So my confidence interval, 30% up to 42%, right? 36 is right in between those two. So from here to here's our 99% confidence interval. Again, what we're trying to say with this, use the idea of a sampling distribution, we're just trying to say that the true population proportion is in here. So that's a pretty big range from 30 to 42. So even a sample size of 500 didn't give us a great job. It did an okay job of estimating, but it would be nicer if we could even get closer than that. We would have to increase this. And you can use sample size estimate formula also to do that same thing here. And the one other thing that I didn't put on here, I want to make sure that everybody gets, when you work with the difference between a T and a Z distribution, there's something called degrees of freedom. Degrees of freedom is something that you may read. It was in the text. It's n minus 1, sample size minus 1. So if you have a sample size of 500, 500 minus 1, right, you would get 499. So degrees of freedom, you'll notice in this case, doesn't make much of a difference. 500, 499, right? Now, when you have smaller sample sizes, that's when you see the bigger differences, even though it's n minus 1. When you look at the chart, the t distribution chart, so degrees of freedom is connected to the t distribution. It makes a bias adjustment on sample size. So again, I'm just throwing this in here because I forgot to remember, I forgot to talk about that earlier, but it is in your book. So again, degrees of freedom, this is something that you do need to know. N minus 1, very simple computation. If you had 25 in your sample, you'd have 24 degrees of freedom. If you had 10 in your sample, you'd have 9 degrees of freedom, so on. Okay, so but we're gonna go ahead and stop there and give you a chance to practice on finding confidence intervals.